Let's look at more rolling without slipping. This time, let's analyze the motion by looking at forces and torque on an object. And let's start by considering any object on a hill. If the hill is very smooth, how will that object behave on the hill? And I have drawn here a square, a rectangular, boxy object, and then I have a round object. If the hill is very smooth, then that's code for there is no friction on the hill. Now, my round objects, I can't turn off friction, but I do have a squarish, boxy object for which I can turn off friction. So let's take a look at this. Let's consider this boxy object. If there is friction and I put the boxy object on the hill, it doesn't move because friction wins. If I turn off friction and I put it on there, watch what happens. It accelerates down the hill. It does not rotate, it doesn't tumble over itself, it just slides. And every point on this object slides with the same acceleration. It doesn't matter if it's the top or the bottom, the back or the front, or the middle. They all accelerate with the same acceleration. Now consider a round object. Now if the round object had no friction, and unfortunately I can't do that, if the round object had no friction, it would also slide straight down. Or if I put it on a flat surface, it will also have no acceleration at all, as all the forces are balanced. Moving it here, and you can see that I have a line drawn on this, moving it here, when I let this go, you're going to notice that because there is friction, it's going to roll. It will translate and it will rotate at the same time. And we looked at that yesterday with the bike wheel being rolled across the tabletop. So watch the try to watch both the center as it accelerates linearly and watch the line as it starts to spin. You should notice that the center, if you can watch this, now let's do that again. Just watch the center and only the center. Now watch the line. And just the line. Don't look at the center. Don't try to follow the center. Try to look at this point on the rim here and see how that goes. It should look like when the point gets to the bottom it slows down, but then when it's at the top it's moving faster. Let's do that again. Watch it. Now, what's happening with this is at the center of mass, gravity, which pulls straight down, being slightly off-center now from the point of contact, where I have the line straight down to the point of contact, it pulls the weight parallel, pulls the puck down the hill. But at the same time, that friction at the point of contact is opposing the potential slide down the hill. That friction at the point of contact is pointing up the hill. So we have these two forces that are acting at different points. We have the weight that acts at the center of mass, and then we have friction that acts at the point of contact, and these two guys are offset from one another. The result being that while the center of mass is accelerating down the hill, the point of contact, being stopped by static friction, causes it to rotate. So let's draw a free body diagram of the situation and analyze the motion of this round object using forces and torque. So we have our puck with the center of mass marked and the point of contact marked. And in drawing the free body diagram, we have the weight that points straight down. Let's call that mg. And we also have the normal force that points from the point of contact through the center, perpendicular to the surface. And we also have friction. Now that friction is static friction because the point of contact is not sliding. Since the point of contact is not sliding, it is in static friction. And we need to remember that for static friction, that is always going to be less than or equal to mu times Fn. That less than makes this situation kind of annoying to analyze using forces. Because we can't just substitute mu times mg cosine theta here like we can for any other object that is actually sliding down the hill. So we're going to have to analyze this motion a little more carefully using both Newton's second law for linear and for rotation, and our goal is to obtain a usable equation for the linear acceleration of the object. So let's start by looking at the linear Newton's second law. Linear Newton's second law has forces acting in the x direction cause the center of mass to accelerate in the x direction. So let's take a look at the forces in the x direction. The forces in the x direction are the sine piece of the weight that we call weight parallel and static friction. So weight parallel being mg sine theta points down the hill, and we have static friction causes the mass to accelerate down the hill. Now we have a problem with this. The problem is we can't know exactly what that static friction is, because remember that static friction is less than or equal to mu Fn. That less than piece says that unless we tilt this hill to be extraordinarily steep so that we reach the limiting case, it's not going to be equal to. It's going to be some number less than mu Fn. So we cannot simply throw mu Fn into there. What we have to do is pause here and take a look at Newton's second law for rotation, which is torque. Now let's take a look at torque. There are two reasonable places to put the point of rotation, point of contact, and the center. For the forces in the x direction, what we've done is we've put the point of interest at the center as we're looking at this guy, because we're looking at the acceleration of the center of mass. So very frequently you will see ACM there for the acceleration of the center of mass. So why don't we put the point of rotation at the center there also? So if we put the point of rotation at the center there, then when we're going to be looking at the torques, what we need is the forces that are a distance away from the center to be adding up for that torque. For the moment, since we have three forces, we'll put all three forces in there for the torque, but then we will systematically eliminate the ones that disappear. So for all of these guys, we're going to have R cross FF plus R cross mg plus R cross Fn equals I alpha. Now, the other benefit of sticking the point of rotation at the center of mass is that our rotational inertia, I there, will also simply be the rotational inertia at the center of mass, which for an object like a disk is a known quantity. Now let's take a look at the left side there, and remember each of those R's, maybe we should call this R1, R2, and R3, that correspond to each the friction, the weight, and the normal force. Let's start with the one on the end there, the normal force. So the normal force acts at the point of contact, just like friction does, and it is a distance, radius away from the center of mass, our chosen point of rotation. But here's the thing with the normal force. R points from the center of mass, our point of rotation, to where friction points, but to where the normal force points, but then the normal force points back along that. So there is no cross there. And for this guy, that cross product is zero because they are not perpendicular. So not perpendicular means that that guy goes to zero. They are anti-parallel. All right, the next one. Let's take a look at weight. The weight acts at the center. The radius from the center to the center, so R2, is zero. So at that point, this guy is zero, so the whole product is zero. So that guy is zero, simply because the R that we have to associate with the weight That is 0. That leaves the radius, r1, from the center out to the point of contact, and this static frictional force. Oh, good. We have another expression for friction that we can use to eliminate the friction in this expression, and that will help us get the linear acceleration of the center of mass. Here's the next point of interest, that alpha over there. As long as this round object is rolling without slipping, then we can make the substitution that we discussed in the previous video, where alpha is a over r. So let's substitute that guy into this equation and solve for the frictional force, because remember, we don't know what the actual number is for the frictional force. So friction is going to be equal to rotational inertia, a center of mass, and then we're going to divide everything by the radius of our object. And now we have an expression that depends on the rotational inertia at the center of mass of our round object, the acceleration of the center of mass, and then the radius of that object. We can substitute this guy in here and then see what we get. So I'm going to have mg sine theta minus I a center of mass r squared and a center of mass. All right, now remember our stated goal is we want an expression where we have a center of mass equals a bunch of things. We want a usable equation that describes the acceleration of the object. And we're going to get that by looking at Newton's second law linear, Newton's second law rotational, and then combining them to deal with the fact that we don't know what the static friction is. So let's bring this expression over to here and then factor out the a, because we want to get that by itself. So I have an a here and an a there, so we're going to factor that out to the side. And that guy just comes along for the ride. And now our last step of algebra. Now, there's one required last step to get to where we wanted to, and then there's one more that is simply done for convention. So if we divide everything by this mess inside the parentheses, we're going to have a equals mg sine theta divided by this stuff. Now, another thing that is typically done is we factor out an m, because what we want to do is we want to see the acceleration. And that will highlight the acceleration. So we end up with a center of mass equals g sine theta over, now if we divide everything by an m, we're going to divide an m there, so that cancels, we're going to divide m there, but then we end up with an m in the denominator down there. Then we're going to have 1 plus I over mr squared. Where if you've got numbers, you got to make sure that you put parentheses around that. All right, and what we have here is now an equation that we can use that we've derived from first principles. Remember, you have to be able to do this because the odds that you get this exact situation all over again are somewhere between slim and none. So you have to take this situation and the way that we've analyzed this and apply it to a new situation that you haven't seen before, but you're going to go through the same process with slightly different forces here and slightly different torques there. But it's the same starting point, and it's the same process through which you're going to go in order to end up with acceleration equals some expression on the other side. Now let's pause here for a second and consider a couple of what-if scenarios. What if we have that air puck situation that I started the video with, where it's not rotating? All right, if it's not rotating, the rotational inertia is 0. And then what we have is g sine theta divided by 1 plus 0. Well, 1 plus 0 is still 1, and then g sine theta over 1 is just g sine theta. So if frictionless block we get back what we have looked at before, and we can expect to get the acceleration down the incline is simply g sine theta. We've already done that. We even did that experiment with the carts on the hills. But what if we have something that is rotating and it's a known shape? So for example, it's that solid disk. Solid disk, the rotational inertia is 1/2 mr squared. What do we get then? What we get is what we would expect to get out of this equation. If we have 1/2 mr squared divided by mr squared, we get a 1/2 down here because the mr squareds cancel each other out. Then we get 1 plus 1/2, which gets us 3/2. And if you're dividing by 3/2, that's the same thing as multiplying by the reciprocal of 2/3. So we get A equals 2/3 g sine theta. What we get is the A center mass is less than g sine theta. It is some fraction of g sine theta, which, as we talked about yesterday, some of the energy, since it's raised up and rolling down a hill, it will have potential energy. Some of that potential energy gets turned into rotational energy. It's hidden in the spin. So therefore, it's not part of the linear, and it will have less linear energy when it gets to the bottom of the hill. Well, in order for it to have less linear energy, therefore, it must have also less linear acceleration. Because the overall, you got g sine theta to play with. And when something is rotating, what that means is the linear piece gets less than it had before, and the rotational piece now gets more than 0. Whenever you do any of these sorts of derivations, it's important to play this little mental game here and ask yourself, what if X is the case? What if I turn off the rotation? What do I get back? Do I get back the linear case that we talked about before? If the answer is yes, then you're probably on the right track. If the answer is no, then you need to go back and most likely you drop the negative sign. Now let's take a look at a specific for instance. What if we have a yo-yo? A yo-yo is sort of an extreme example of what I'm talking about. And what I mean by extreme is the angle of the hill for a yo-yo. I mean, look at this. This string here is the hill, except that hill is a vertical hill. So if it's on a vertical hill, that means the hill's angle is 90 degrees. That's an extreme hill. Let's take a look at that equation. Let's use that equation and find out what the linear acceleration of this yo-yo is going to be. Now, since we already derived the equation, I'm not rederiving that. That's what that board is. Let's just take that equation at the very end and plug numbers into it and see what we get. So A equals g sine theta over 1 plus I over mr squared. Since, I've given things in a mishmash of units here, let's just stick things in with grams and centimeters. That way this guy will be 90 centimeters per second. And this axle here is going to be 1/2 centimeter. That means the gravity that we're going to be running with is 980. The sine of the angle is 90 degrees. 1 plus 960 divided by 120 times. Now that r there is not going to be the radius of the thing as a whole. It's going to be the radius around which it's spinning. If you remember back far enough, that r is the radius at which the frictional force acts. So that's going to be that little tiny r there. That's going to be 0.5. And don't forget to square it. Now, when you stick those guys in the calculator, you should get 29.7 centimeters per second squared. What this is saying is the yo-yo is significantly slowed down by the fact that it has to rotate on a string instead of just dropping it. If we just dropped it, the acceleration would be 980. But now it's going to be a significantly smaller fraction than 980 because we've got these two giant disks on either side of a tiny axle. So those two giant disks produce a rotational inertia of 960 centimeters per second squared, centimeters squared. And that tiny axle has a pretty serious effect on the fact that this torque from the friction it's a small torque there. If I put it closer to the rim, it would be a different effect. Now, for this mathematical case, we are assuming two things. Number one, that the string is uniformly wound, it's got no tangles in it, and 2, it is infinitely thin. If you've ever played with an actual yo-yo, you know that the string has thickness. So we're ignoring a few things here. All right, let's calculate the translational speed of the yo-yo center mass just as it's reaching the bottom of the string. Now, if I've thrown it down at 90 centimeters per second, and then it continues to accelerate down at about 30 centimeters per second squared, and the string is 110 centimeters long, what I have here is a linear kinematics problem. It's a Wolfenstein. So VO is 90. VF is what I'm looking for. S is going to be 110. And the acceleration I just found at 29.7 centimeters per second squared. We'll get to time later. So given that we don't care about time right now, grab your favorite kinematics equation and jam numbers into it. What we're looking for, 90 squared plus 20 times 2 times 29.7 times 110. Don't forget to take the square root. And you end up with 121 centimeters per second. Now, there are more things that I could ask you to find. What I'm looking for here is a physics problem that incorporates multiple aspects of physics. And we started out with Newton's second law plus rotational aspect of Newton's second law. That's where we got this entire expression. We did that back on a previous board. And now we have linear kinematics down here. Now for part C, we're going to have angular kinematics, or the connection between linear and angular. The angular speed there is going to be the linear speed divided by that axle radius around which it's spinning. So that'll be 242 radians per second squared. Radians per second, sorry. Now we're also assuming that it was rotating a little bit as it left your hand. Again, if you've played with a yo-yo, when you let go of it, it's going to be rotating a little bit as it's falling down. And then as it falls down farther, it will be rotating faster and faster and faster, and that rotation speeds up considerably because this radius is so small. All right, the other aspect of kinematics, and we can go back to our linear kinematics here to find the time. So VF equals VO plus AT, 121, 90, 29.7 T. And it'll take a smidge over a second to reach the bottom of the string. Now, yesterday we looked at an object that was rolling down a hill through the lens of conservation of energy, which is a different way of solving a very similar problem, but avoids the messiness of the in-between. So let's look at that again and say to ourselves, self, at the beginning here of the top, what type or types of energy does it have? And down at the bottom, what type or types of energy does it have? Well, at the top, I threw it down with a linear speed, and I've also given it a rotation as it leaves my hand, and it's high up. So it's going to have translational kinetic, rotational kinetic, and potential up here. Now, as it reaches the bottom, just before it runs out of string to unwind, it will be translating. That's the entire point of this guy right here, is it is accelerating linearly, so it is moving linearly. And the point of this part is, by the way, it's also rotating. So when we look at conservation of energy, we will have translational, rotational, plus potential at the beginning, and then at the end, all of that potential has been turned into translational and rotational. Now let's take a look at slightly more specific particulars, where we have 1/2 mv squared, and we have 1/2 I omega squared, and we have mgh, and then we have 1/2 mv squared and 1/2 I omega squared, at the end. Now remember, as long as it's rolling without slipping, we can get rid of these omegas and replace it with v squared over r squared. And the same thing here, v squared over r squared. And remember, that r is not the total radius of the outside of the yo-yo. That r is how far is it from the center to the point of rotation. And from the center to the point of rotation is this half a centimeter. So what we're looking for is the v way over on the other side. And substituting in all the numbers that we have 1/2, 120, 90 squared plus 1/2, 960. 90 squared over 0.5 squared plus 120, 980, 110. And that's all of the information at the beginning. And then at the end, 1/2, 120 plus 1/2, 960, 960 over 0.5 squared. And I factored out the v squared because that v squared is common to both terms on the right side. Now, when you plug in the numbers, the last thing that you're going to have to do is divide by the coefficient on the right of the v squared and then take the square root. And when you do that, you end up with numbers that I actually have to look at as I copy down. 2,897,4,000 equals 1980 v squared. All right. 28,974,000 equals 1980 v squared. So divide by 1980, take the square root, and you'll discover that we've got the same speed that we got before. And this time we managed to do it in one step. Notice last time we had to go through the acceleration and then kinematics. We had dynamics and kinematics produces the same result as conservation of energy. Sometimes you want the one, and sometimes you want the other one. Which one you want depends on the situation that you're looking at and what you need to find. In this video, we looked at a situation in which gravity pulled the yo-yo down and tension in the string pulled up on it, and that mismatch between those two forces produced the combination of linear and rotational motion that we see in a yo-yo. In the next video, we will take a look at a couple of situations that involve, instead of having gravity pull in one direction and you pull in the other direction, we will just set the round object on a surface and pull it sideways from a couple of different points on the object and analyze that motion, again looking at the forces that produce the combination of linear and rotational motion that we call rolling.